Hello students, welcome to another section of topological space. In this section, we are deals with which are the properties preserved under continuity. That means a property of a topological space. So a property of a topological space is said to be preserved under continuous map if the continuous image of the topological space also has a property. That means, suppose we have a topological space x2, okay, and you have a map and yu be another topological space and f is a mapping from x to y. Then you consider the range set f of x. So f of x and u restricted to f of x will be a topological space, right? Subspace topology of y. So a topological property is said to be preserved under continuity means, suppose x2 has a property. So let A be a property of x. And if f of x also has the same property, then we say that that property is preserved under continuity. For example, suppose x2 is a discrete space. Okay, and f of x and u restricted to f of x is also is discrete space. That is this topology, induced topology is also a discrete topology on f of x. Then we say that that property is called preserved under continuity. Okay. Examples are compactness and Lindelofness. Lindelofness are properties which are preserved under continuous map for the topological space. That means if x2 is a compact space and f is a continuous map from x to y, then f of x is also compact in y. Similarly, we can prove for the Lindelofness also. So we prove as a theorem. Let x to be a compact topological space, and f from x to y be a continuous onto function, then y is compact. Ontoness means the range is nothing but codomain. Instead of proving f of x, we will prove the whole y. For that, I assumed that f is onto. Okay, f onto allengil we need only prove f of x is. If f is not onto function, we want to prove that f of x is compact. Since f is an onto function, its range is nothing but the whole codomain. Therefore, we need only prove that y is compact. Okay. Or I can say that is continuous image of compact space is compact. This is the meaning of this theorem. Continuous image of compact space is compact. Okay. So to prove this, let f from x to y be a continuous onto map and x be compact space. What is we want to prove? Y is compact. Our claim, y is compact. How will you prove a set is compact, a space is a compact? We want to prove every open cover of y has a finite subcover. So let V be an open cover of y. Okay. Then V is nothing but collection of open sets in y. Okay. Then for every V in script V is an open set in y and y is contained in union V in script V. Okay. Now corresponding to, we have the space y and we have some open sets V. For avoiding confusion, I consider some V alpha, okay? Then V alpha is open set in Y, then union alpha, V alpha. Okay, that will be enough. Y will be containing union alpha, V alpha because collection V alpha form an open cover. V is nothing but collection of V alphas. Okay. So, V alphas are open sets in Y. And what is F? F is a mapping from X to Y which is onto. Onto means every element in Y will have pre-image. Okay. So since each V alpha is open in Y and we have assumed that F is a continuous map, by the definition of continuity, inverse image of open set is open. So F inverse of each V alpha will be a subset of X and which will be open in X because F is continuous. Right? So since F is continuous, for every alpha, comma, F inverse of V alpha is open in capital X. I take F inverse of V alpha is equal to U alpha. Take F inverse of V alpha is equal to U alpha. Okay. So we clear? You consider an open cover, arbitrary open cover of Y, which is nothing but collection of open sets V alphas. Since each V alpha is open, F inverse of V alpha is open in capital X because F is a continuous map. Ready? So you take F inverse of U alpha as another name by U alpha. Right? Now consider collection U alpha in an indexed set. Okay? Collection U alpha. What is U alpha? F inverse of V alpha. And you know every U alpha is open in capital X. Then what will be collection U alpha? Collection U alpha form an open cover for X. Okay. So since X is compact, every open cover of X will have a finite subcover. Then since this collection form open cover, collection U alpha has finite subcover. That is U alpha 1, U alpha 2, etc. U alpha n, finite number of elements from this collection. And that is be the subcover of U alpha to cover X. So that means capital X is contained in union I equal to 1 to n U alpha. These finite number of elements can cover whole X, capital X, whole space capital X. Okay. And corresponding to these U alpha 1, U alpha 2, etc. U alpha n. What is U alpha I? U alpha I is F inverse of V alpha I, right? So corresponding to these alpha 1, alpha 2, etc. alpha n, we can consider the corresponding inverse images. F inverse of V alpha 1, F inverse of V alpha 2, etc. Okay, we will prove that F inverse of V alpha 1, F inverse of alpha 2, etc. F inverse of V alpha n be the finite subcover for Y. Okay. How will you say that? So now we claim the subcollection F inverse of V alpha 1, F inverse of V alpha 2, etc. F inverse of V alpha n is a finite subcover. Clearly it is finite, it is a subcover. It's a subcover of sorry, this is not our claim, I'm sorry. Now we claim that collection corresponding to these F inverse of V alpha i's, I consider the V alpha i's. V alpha 1, V alpha 2, etc. V alpha n is a finite subcover for collection V alpha of Y. So we have taken collection V alpha is the open cover of Y. We need to prove that this collection has a finite subcover. Now I will claim that corresponding to these F inverse of V alpha is, you consider F V alpha is only. That is V alpha 1, V alpha 2, etc. V alpha n. We will prove which is the finite subcover, which is a finite subcover of collection V alpha to cover Y. So we need only prove that clearly this is a subcollection of V alpha, and we need only prove that this Y will be contained in union of these V alphas, right? So that is Y is contained in union I equal to 1 to n V alpha I. This is our claim. Okay, so I take an element Y. Let small y is an element in capital Y. Since f is a mapping from x to y, we assume that our function f is onto. So for every y in capital Y, it has a pre-image. Since f is onto, comma, there exists some x in x such that it has the pre-image f of x is equal to y. Okay. Since f of x is equal to y, so we get corresponding to y in y, we get an element x here, that x is mapped into y. Since x belongs to capital X and whole capital X is contained in union I equal to 1 to n u alpha i's, what will you have? Since the whole X is contained in union of these finite number of elements, the small x is also contained in this union. Therefore, x belongs to union I equal to 1 to n u alpha I, since capital X is contained in union I equal to 1 to n u alpha I. So x belongs to union means x belongs to any of some u alpha I for some I. So x belongs to u alpha I for some I means x belongs to, what is u alpha I? U alpha is nothing but inverse image of v alpha I. F inverse of v alpha I for some I. So which implies f of x belongs to v alpha I for some I. So what is fx? Fx is nothing but y. So y belongs to v alpha I for some I. So corresponding to every element y in y, we get that y belongs to v alpha I for some I. So whenever y belongs to v alpha I for some I, y will be belongs to this I is nothing but 1, 2, 3, etc. n. We consider only finite number of i's. Since u alpha 1, u alpha 2, etc., u alpha n is finite. Only finite number of elements. Okay. So y belongs to union I equal to 1 to n v alpha I. So from y belongs to y belongs to this union implies y is contained in union I equal to 1 to n v alpha I. So whole y space is contained in union of finite number of v alpha 1, v alpha 2, etc. v alpha n. That means our y is compact. It is a finite subcover for v alpha. Therefore, every open cover of y will have a finite subcover, which implies y is compact. By the same similar arguments, we can prove that continuous image of Lindelof space is Lindelof, or the property Lindelofness is also preserved under continuity. Continuous image of Lindelof space is Lindelof, or Lindelofness is preserved under continuity. That means, how will you prove this? Let f from x to y be a continuous onto map, where x is a Lindelof space. Okay. We want to prove that, we have to prove that y is also Lindelof. What is the definition of Lindelof space? Every open cover has finite subcover. So let collection V alpha be an open cover of Y. We need to prove that it has a finite subcover. Okay. Since each V alpha is open in Y and f is continuous, implies f inverse of V alpha is open in capital X. Inverse image of open set is open. Okay. Since for every V alpha, f inverse of V alpha is open in X means you can consider this f inverse of V alpha as some U alpha. take with the same proof above, U alpha equal to F inverse of V alpha. Then each U alpha is open in X. Consider collection U alpha, which is an open cover, which is an open cover of capital X. Since capital X is Lindelof, what is the definition? Every open cover of X has countable subcover. So this U alpha is an open cover, means it has a countable subcover, comma, U alpha, collection U alpha has a countable subcover. Countable subcover. That is some U alpha 1, U alpha 2, etc., U alpha n, etc. This countable means that elements can be arranged as a sequential order. But it is not finite. That means it is infinite, but it has a particular order. Okay. And X is contained in union I equal to 1 to infinity. I have to write 1 to infinity because it is countable. U alpha I, not 1 to n. 1 to n means it is finite. For the compactness, we need to write I equal to 1 to n. For the Lindelofness, we want countable subcover. Therefore, it is y equal to 1 to infinity. Okay. Okay. So, whole X is contained in I equal to 1 to infinity U alpha I. So, instead, corresponding to these alpha 1, alpha 2, etc., alpha n, etc., this countable collection, we can consider the inverse images. Now, consider since U alpha is our inverse image of corresponding V alphas, I consider V alpha 1, V alpha 2, etc., V alpha n, etc. We will prove which is a countable subcover of collection V alpha to cover Y. Clearly, each V alpha n's are open. Okay, because these are collection elements from collection V alpha. Collection V alpha is an open cover of Y. Therefore, every V alpha will be open. Okay. So, how will we prove this? This is a countable subcover for Y. That is, we want to prove that Y is contained in union I equal to 1 to infinity V alpha I. This is we will not only prove. So, I take an element from Y. So, let small y is an element in capital Y. Again, since F is an onto map, there exists some x in capital X such that f of x is equal to y, since f is onto. And we have whole capital X is contained in union I equal to 1 to infinity U alpha I. Okay. Therefore, X belongs to union I equal to 1 to infinity U alpha I. Because whole X is contained in this, X is a small element in capital X, therefore small x is also belongs to this union, which implies X belongs to union means X belongs to U alpha I for some I equal to 1, 2, 3, etc. Countable indexing set. So, X belongs to U alpha I means X belongs to, what is U alpha I? It is nothing but F inverse of V alpha I. So, which implies F of X belongs to V alpha I for some I equal to 1, 2, 3, etc. So, which implies F of X is nothing but Y. Y belongs to V alpha I for some I equal to 1, 2, 3, etc. Which implies Y belongs to union I equal to 1 to infinity V alpha I, because it belongs to any of the countable number of V alpha I means it must be belongs to their union also. So, which implies whenever Y belongs to Y belongs to this union, means Y is contained in union I equal to 1 to infinity V alpha I, which implies V alpha 1, V alpha 2, etc., V alpha n, etc. is a countable subcover for collection V alpha to cover Y. That is, Y is Lindelof. So, same proof. It is exactly same as compactness. Only difference is finite subcover and countable subcover.